Hello students, this is your chemistry teacher. Today we will be discussing on the rest properties of the D block elements one by one. So let's get started. So first of all, we will be discussing on the variation of M2 plus M standard electrode potential or standard reduction potential. So before coming to the topic, I would like to give you the recapitulation, a short recapitulation of reduction potential concept. So in class 11 we got to know that reduction potentials value actually gives the idea that how easily or how spontaneously the elements get reduced. Okay, so on the basis of this concept we arranged all the elements from positive reduction potentials to negative reduction potentials coursing through hydrogen, where we had taken potentials of hydrogen, reduction potential of hydrogen, that is E H plus hydrogen, that is equals to 0 volt. Okay, so above the hydrogen, the elements, if the elements exhibit more positive reduction potentials, if the elements exhibit more positive reduction potential, that signifies that the reduction of that element occurs more spontaneously. That means element is more oxidizing, or you can say element has more oxidizing power, or you can say element is a better oxidizing agent, because as we know that oxidizing agent accepts electron and reduce itself. So obviously if the process of reduction for an element becomes spontaneous, we can say that that element is a better oxidizing agent. Similarly, if we get a more negative reduction potential value, or you can say less positive reduction potential value, that signifies that the reduction occurs, or reduction of that element occurs less spontaneously, or you can say in another way that oxidation occurs more spontaneously. And we can say, or we can assign that that element is a better reducing agent, or that element is more reducing, because reducing agent reject electron and oxidize itself, right? So in case of more positive reduction potential value, that will signify element is more oxidizing or better oxidizing agent. And if the reduction potential value is more negative or less positive, then you can say that that element is more reducing or better reducing agent. Okay, another important thing that you have to look on, that if M2 plus has higher hydration enthalpy, where M represents a transition element or D block element, and M has lower ionization enthalpy, then the process that will be spontaneous is M2 M2 plus. Because if M2 plus has higher hydration enthalpy, obviously M2 plus will be very much stable, because a lot of water molecules will be surrounded around this M2 plus ion, and vast amount of energy will be released, and M2 plus will be very much stable. And at the same time, if M has lower ionization enthalpy, then M will lose the electron very easily, and that's why M2 M2 plus process become more spontaneous, right? So two things you have to look on. Number one, M2 plus has to be very stable. That means M2 plus must possess higher hydration enthalpy, and M has to be M must show the low ionization enthalpy value. In that case only you can say that M2 M2 plus process is spontaneous. Now in the second case, if the opposite process occurs, like if M2 plus has lower hydration enthalpy and M has higher ionization enthalpy, then what happens? Then obviously M2 plus is not going to be stable, and at the same time M is not going to lose the electrons and form M2 plus. So M2 M2 plus process will not occur in that case. In that case opposite process will occur, like M2 plus will accept the electron and convert it into M. Okay, so in the second case, again I am repeating that M2 plus, if M2 plus has lower hydration enthalpy, okay, and M has higher ionization energy, then M2 plus will be converted to M. Okay, now on the basis of this concept, if I want to solve, if we want to solve a question like what is the reason behind the positive value of E naught M2 plus M for copper, where E naught copper 2 plus copper value is given 0.34 volt. From the value itself you can see that it's a appreciable positive value, appreciably highly positive value, and we have already discussed that positive value of reduction potential indicates that the element has a better oxidizing nature, or element is a better oxidizing agent. Okay, and at the same time we have concluded that uh, the process of reduction becomes more spontaneous. Okay, so for this reason copper 2 plus here is accepting 2 electron and converting into copper, and it's a reduction process. We have already discussed that if the reduction potential value is highly positive, that indicates the reduction process becomes more spontaneous. So that's why copper 2 plus is participating into the reduction process and it is accepting 2 electron and converting into copper. Now the second case is that then now you have to look on the second case, that due to high ionization enthalpy of copper and low hydration enthalpy of copper 2 plus, these two factors are responsible for the above process. High hydration enthalpy, high ionization enthalpy of copper, you see in the second case ionization enthalpy of M is higher and hydration enthalpy of M2 plus is lower, and that's why M2 plus to M this process is occurring. So sorry, so copper 2 plus, since the copper has the higher ionization enthalpy and copper 2 plus has lower hydration enthalpy, so copper 2 plus will accept 2 electron and convert it into copper. Okay, so due to the three reasons, due to two reasons, this process copper 2 plus to copper is occurring. Number one, high ionization enthalpy of copper, and number two, higher high ionization enthalpy of copper, and number two, low hydration enthalpy of copper 2 plus. These two processes are responsible for this above process of copper 2 plus to copper. Okay, now let's discuss the magnetic property of transition elements. So far we have already learned that transition elements are those elements which contain one or more unpaired electrons in their valence shell, right? There are a lot of unpaired electrons present in the d orbitals of their valence shell, and for this reason they are paramagnetic in nature, because paramagnetic substances contain unpaired electrons in their valence shell or contain unpaired electron in their systems, right? Number two point is, among the first transition series, uh, if I talk about the chromium that has the electronic configuration 3d54s1 and manganese that has the electronic configuration 3d54s2, contains maximum number of unpaired electrons, because chromium and manganese both contain 5 unpaired electrons in its valence shell, and for this reason maximum paramagnetic behavior are being shown by this chromium and manganese. Okay, because paramagnetic behavior or paramagnetic nature paramagnetic nature totally depends on the number of unpaired electrons that are present in the valence shell. Since chromium and manganese contain maximum number of unpaired electrons in their valence shell, so obviously they will exhibit maximum paramagnetism or maximum paramagnetic character. Okay, now this paramagnetic character of the transition elements is measured by a unit called Bohr magnetism or Bm. Mathematically it is expressed by mu. Mu is the symbol of magnetic character. Okay, paramagnetic behavior. Mu is equal to root over of n into n plus 2 Bm, that means Bohr magnetism, or you can say mu is the magnetic moment. Okay, mu is called the magnetic moment, that is equals to root over of n into n plus 2 Bohr magnetism, where small n represents the number of unpaired electrons present in the valence shell of that element. Okay, since we know that manganese contains 5 unpaired electrons in its valence shell, so for manganese the value of magnetic moment mu will be equals to root over of 5 into 5 plus 2. This root over of 5 into 5 plus 2 will give you the value 5.91 Bohr magnetism. Now let's discuss the catalytic property of these transition elements. So first of all, to be a good catalyst, what are the characteristics for an element that that has to be maintained for an element to show a better catalytic property? Catalytic property to for an element, if the element want to show a better catalytic property, the element must contain a large surface area. Element must have a large surface area. Number two, the element has to be the element has a tendency to exhibit variable oxidation state. If the element has a tendency to exhibit variable oxidation states, they can act as a good catalyst. At the same time, if there are a lot of unpaired electrons, or if there are vacant orbitals present in the valence shell of those elements, then those elements can act as a good catalyst. We have already learned in some processes, like in some organic processes, we have learned that palladium, platinum, iron act as a good catalyst, because these are all transition elements and they have large surface area, number one. Number two is they have a great tendency to exhibit variable oxidation states that we have already discussed in the properties of d block elements, that d block elements have a great tendency to exhibit a variety of oxidation states. Okay, and number three, they have vacant d orbitals. So due to these three reasons, they act as a good catalyst, because all the catalytic process occurs in the surface, right? So if the surface area is large, then obviously those elements can act as a good catalyst. Transition element have a very large surface area, and that's why they can act as a good catalyst. Moreover, transition element can exhibit a variety of oxidation states, and that's why catalytic process becomes easy for the transition elements. Number three is, for transition elements there are vacant d orbitals present, and these vacant d orbitals will be utilized in the process of catalysis for those elements that act as a catalyst, right? So for all these reasons, the transition element act as a good catalyst. Now let's discuss the formation of the colored ions and interstitial compounds that the transition elements are forming. So number one point is that if I ask you one question, so why do the transition elements show color? Okay, what is the reason behind it? Why do the transition elements show color? We have already observed in your lab that there are some salts, or maximum salts of transition elements are colored, like copper sulfate is of blue color, iron chloride or ferric chloride is of brown color. Okay, copper sulfate means copper 2 plus, iron chloride or ferric chloride means Fe3 plus. So all these ions of transition elements, or you can say all the salts of the transition elements, show color. What is the reason behind it? Reason is that we know the transition elements have d orbital. How many types of d orbitals are possible? 5 types: dxy, dyz, dzx, dx square minus y square, and dz square. These 5 d orbitals have the same energy. Initially they have the same energy, and that's why they are called degenerate d orbitals. But when the transition elements form compound with different anions, like if I give you example like CuCl2, where copper is forming compound with Cl minus, FeCl3, CuSO4. In these compounds, when the transition metals will form these type of compounds, or when transition elements will combine with anions like Cl minus, SO4 2 minus, etc., the 5 d orbitals that are called degenerate d orbitals, these degenerate d orbitals will be splitted up into two set of orbitals: the lower set of orbitals, lower set of d orbital and higher set of d orbital. Lower set of d orbital contains dxy, dyz and dzx, and higher set of d orbital contains dx square minus y square and dz square. Now the electrons always try to remain in the lower set of d orbitals, and when these electrons that are present in the lower set of d orbitals absorb energy from environment, it will go to the higher set of d orbital, and when it will reach the higher set of d orbital, they will be unstable. Okay, and since they are unstable, they will try to return in the lower set of d orbital by emitting the same amount of energy that they absorbed in the initial time of transition from lower set to higher set of d orbital. So that the same amount of energy will be released in the process of returning of those electrons from the higher set to the lower set of d orbitals. Okay, and that's why the energy will be released in this process. Okay, this energy is released in the form of light, and that light strikes our eyes and we see the color of those elements. Okay, and this is the reason why the transition elements show the color. Okay, now another important property for these d block elements or transition element is the excellent ability to form interstitial compound. Okay, so first of all, we know that in the crystal structures of the transition metals there are some vacant space due to crystal defect. In the solid state chapter, we learned that due to crystal defects there occurs some vacant spaces in the crystal structure of the elements. Similarly, following the same trend, transition metal crystals also contain some crystal defects, and due to this, there are a lot of vacant spaces present in the crystal structures of the transition elements. Okay, And in these vacant spaces, a small atoms like boron, carbon, nitrogen can occupy these interstitial spaces or these small spaces and form interstitial compound with the transition elements. If I give you example, like in the crystal structure of titanium, small atom like carbon can fit into the crystal structure and form titanium carbide, TiC. Similarly, in the crystal structure of tungsten, if small atom like carbon fit in the vacant spaces of the crystal structure of tungsten, then tungsten carbide is formed, right? So these are some important transition interstitial compounds of the transition elements like titanium carbide, TiC, and WC, tungsten carbide. Okay, now let's discuss the ability to form alloys and complex and oxoanions. So for the transition elements, we know that transition elements can mix with another transition metals to form some alloys. First of all, we have to know what are alloys. Alloys are called substitutional solids. That means if a metal, or if in the metal structure some metal atoms are replaced by another metal, or if two metals are mixed together, then alloys are formed, right? So if I give you example, like here you can see, here it is a pure metal crystal, metal of copper, crystal structure of copper that I have colored in red circle. And if we mix zinc in the pure metal of copper, then zinc will replace some copper elements or some copper atom from the crystal structure, and there will be a alloy form that is called brass. That will be a perfect combination of zinc and copper. Now one thing you have to understand, that every metal cannot replace every element from its crystal structure. Only those elements can replace a particular element if the elements have the same type of size. Okay, zinc and copper have the similar size, atomic size, then and for this reason why we can replace copper atoms by zinc atoms. Okay, and brace, that means the formation of this brace alloy is done. Okay, so two things: we mix the metals to form alloys, and the elements which are mixed have to be similar in size. Okay, now the second property that for the transition element is that the formation of oxides or oxoanions. The transition metals form oxides or oxoanions of the type MO, MO2, MO4, M2O3, M2O5, even M2O7. Okay, where M represents the transition elements. If I give you example like CrO4 2 minus, it's oxoanions or oxides of chromium, okay, of the type MO4. Clear? So these are some examples of the form of the type of oxides and oxoanions that are formed by transition elements. Okay, another important features that I have already discussed in the common features of, in the list of common features of this d block element, that they have the excellent ability to form complex compounds. Why they have the excellent ability? Because of the smaller size, number one. Number two, high positive charges, and for this reason they can easily combine with different anions to form complex compounds. Now if I discuss the covalent character and the basic character of the oxides or oxoanions of transition elements, like if I give you example like CrO, Cr2O3 and CrO3, in these three oxides of chromium you can see the anion is same, that is oxide ion O2 minus, but the cation, that is chromium, has different oxidation states in different compounds. In the first compound, chromium has oxidation state +2, in the second one it has the oxidation state +3, and in the third one it has the oxidation state +6. Okay, you know how to calculate the oxidation state of an element in a compound, right? Now you see, according to Fajans rule, we have already learned that more the positive charge of the cation, more will be the neutralization between the cation and anion, and more will be the covalent character of that compound. So obviously if we move from left to right, from CrO to CrO3, the oxidation states of chromium, central chromium, is increasing. That means in first compound it is +2, then it is +3, then it is +6. So oxidation state is increasing, and for this reason there will be more neutralization between the positive charge of the chromium and the negative charge of the oxide, and for this reason the covalent character increases from left to right. Similarly, if we want to discuss the basic character of these oxides, then we will find that basic character decreases from left to right. That means from CrO to CrO3. Why it is happening in this way? Because we know that basic character is nothing but the ability to liberate the oxide ion, right? So as the oxidation state of the transition element, that means chromium, is increasing from +2 to +6, the oxide ion will be tightly bounded with the chromium atom or the cation there, and for this reason the oxide ion is not gonna leave the compound and basic character decreases. Okay, so this is all about the important topics of this chapter. The rest topics of D block, that will be coming up in the next week. Till then, thank you so much for watching this video. Thank you.